Section 12.1 Systems of Linear Equations, Substitution and Elimination Methods here. An example where something like this shows up is, say, a movie theater sells adult movie tickets for $9. Senior tickets are $7. One evening, the amount of ticket sales reached $2,760. 380 tickets were sold if X represents the number of tickets sold at $9. Y represents the number of tickets sold at $7. Write an equation that relates to the variables. Well, the revenue, what's coming in here, we would have 9 times however many adults came. That would be how much money the adults would bring in. Plus 7 times however many seniors there are makes a grand total of $2,760. If we know that there's 280 people total, the adults plus the seniors are going to equal that 280. Here we have a system of equations. If we wanted to know how many adults there were and how many seniors there were, all we would have to do is solve this system. Another example where something like this shows up is at an intersection. So if we're, say you're sitting at an intersection, and we've got our intersection here. We've got some cars sitting there. This car's going through. This car's just getting there. This car's waiting to see what he can do. And then we've got lights, stoplights there. Well, cars that are going in, cars that are coming out. The way that these lights are set up is to actually follow a system of equations. So to keep this flowing as good as possible, we want to satisfy a system of equation where some are coming in, some are coming out, and getting a total. That would be another example where systems of equations are used. So a system of equations is a collection of 2 or more equations, each containing 1 or more variables. A solution is the values for the variables that are solutions of each equation. And to solve a system of equations means to find all the solutions. So a system, there would be a collection or a few equations. The solution is the numbers that are going to work in all those equations. And to solve it means to find those numbers. Some more vocabulary: when a system of equations has at least one solution, it's called consistent, meaning it can work out. When a system has no solutions, it's inconsistent. Sometimes we can get equations, a set of equations, a system of equations, where we can't find a solution that works for all of them. Then it's inconsistent. An equation in variables is said to be linear if it's equivalent to the form a1x1 plus a2x2. What this is saying is we have distinct variables here, and the a's in front are just numbers. And at least one of the a's is not 0. So if each equation in a system is linear, then we have a system of linear equations. Possibilities for an equation with 2 variables. If we have 2 variables, then we just have a line. If you think of 2 lines or 2 equations, 2 lines could intersect at exactly one spot. They could intersect never, in which case they're inconsistent, or they could actually be the exact same line, and then they're consistent and dependent on each other. So doing some practice, solve the system by graphing and using substitution. Here, if we're going to solve this system by graphing, to get a real good idea what's happening, we're going to need a fairly accurate graphing calculator. So if we take that system, which was x plus 2y equals -7, graph that line, and then x plus y is equal to -3. I'm just doing it on here so that we can see a real accurate graph versus a sketch. It looks like a solution is right here, which is about 1, -4. So I'm going to say graphically, looking at the graph of these 2 lines, we do have a consistent set of equations, and the solution is going to be at 1, -4. So again, from graphing it, our solution came out to be 1, -4. There's where our solution was. Now substitution, let's say we're going to solve this algebraic. We already solved it graphically. If we're going to solve this algebraically by substitution, that would say take one of the equations and solve for one of the variables. So if I take the second equation here and solve for x, that would mean x is equal to -y minus 3. If this is what x is, this quantity over here, I'm going to take that and I'm going to substitute it into this first equation. So I'm going to take what x is equivalent to, the -y minus 3, I'm going to replace the x with that and substitute it in, plus 2y is equal to -7. The benefits of this, now there is only one variable. I can combine them. Y minus 3 is equal to -7, so y is going to equal -4. Once I find the y value, I've got to go back to find the x value. X is equal to -4 minus 3. X is equal to 4 minus 3, or 1. So our solution, our x value came out to be 1, our y value came out to be -4, which does match the solution we found graphically. One like this, again, solve this graphically. If I'm going to solve it graphically, I'm going to need to have a pretty good sketch of what the graph is so I can find the intersection. So again, I'll go over to graphing calculator, and this time we are graphing 2x plus 4y is equal to 2/3, and then 3x minus 5y is equal to -10, like that. Here I see the intersection right here, -1.6671. So I got the two lines, I have the intersection, -1.6671. -1.6671. Now, that was off of the graph, that approximation. Let's see if our algebra will actually come out to get us the same answer. So by substitution means we're going to have to solve for a variable. If I take, doesn't really matter, let's say I take this one right here. To solve for a variable, in the 2x plus 4y is equal to 2/3, I'm going to go ahead and solve for the x, so I'm going to divide everything by 2 to get the x by leading term or leading coefficient of 1, and then plus 2y dividing by 2 is equal to 2/3 divided by 2 is going to be 1/3. Solve for the x. X is going to be -2y plus 1/3. Now that I have what x is equivalent to, I can go and substitute it in to this equation. So we have 3 times, well, our x is -2y plus 1/3 minus 5y is equal to -10. Now I have only one variable here. I'm going to go do a little bit of work to try to figure out what that variable is. And so -11y is equal to -11. Y is going to be 1. So far it checks out. Now I go back to here to plug that in. X is equal to -2 times 1 plus 1/3, which is -6/3 plus 1/3 equals -5/3. And -5/3 is -1.667. So my solution, -5/3, 1. That should work in either one of these equations. if I just wanted to double check or triple check, because I already found the answer graphing it, we'll go ahead, we'll put that into here to check one of them. 3 times -5/3 minus 5 times 1. Does that equal -10? Well, this is -5 minus 5, which yes, that does equal -10. This one solved the system by graphing and using elimination. So again, let's go over to our graphing calculator so we can get a really good approximation of this. X minus y is equal to 5, and -3x plus 3y is equal to 2. Well, when I look at this, I've got two lines that are parallel to each other. I think the answer is going to be inconsistent because they're never going to cross. So when I'm doing this one here, the answer should be, from graphically, it should be inconsistent. Let's use algebra to check that out. We're going to use elimination on this one. The elimination, the way that works, we want the coefficient in front of the x to be the same. So I would take this first equation, multiply both sides by 3. So when I do that, on that first equation, I have 3x minus 3y is equal to 15. Here, the coefficient is almost the same, so I'm going to add this second equation to the first equation. When I do that, -3x plus 3x is going to give me 0 x's. 3y minus plus a -3y is going to be plus 0y is equal to 2 plus 15 is 17. This is saying 0 is equal to 17. Is that true? Definitely not true. I came up with something that was inconsistent. My answer is inconsistent. There's no real solution for this. Now, a system of 3 linear equations with 3 variables. Some possibilities for solutions include one solution, so we might have one answer. We might have no solution, it's inconsistent, or there might be infinitely many solutions. Kind of like before, we can either have one answer, no answer, infinitely many. These types of linear equations or systems are typically solved via elimination. And so if we look at this system, 2x plus y is equal to 4, -2y plus 4z is equal to 0, 3x minus 2z is equal to -11. There's our system right there. So we're going to solve this by elimination. What I'm going to do first, I'm going to try to eliminate one of the variables. I'm going to do that with this first equation. If this y was a 2, when I would add those together, that would go away. So I'm going to take this first equation. I'm going to multiply this first equation by 2. If I do that to both sides, I'm going to get 4x plus 2y is equal to -8. The second equation, -2y plus 4z is equal to 0. Now I'm going to add these two together so the y's go away. Elimination is what that is. 4x plus 4z is equal to -8. Now I have this equation with x's and z's. If I were to take this last equation, times it by 2, then my z's would be the same but opposite. So I'm going to do that. I'm going to have 6x minus 4z is equal to -22. Again, I'm going to add these together. That'll make the z's go away. So I get 10x is equal to -30, which means x is equal to -3. There is one of my variables that I found. How am I going to go about finding the other variables? Well, I'm going to backtrack here. If I go back to this very original equation, 2 times x plus y. I already have my x value, so I'm going to use that x value, 2 times negative 3 plus y is equal to negative 4. Negative 6 plus y is equal to negative 4, so y is going to have to be equal to 2. Now I found another answer. I can either use this and this equation to find my z, or I could use this and this equation to find my z. It doesn't really matter. I'll go ahead and use this 3x minus 2z. So 3 times the x value that I found is negative 3 minus the 2z supposedly equals negative 11. Negative 9 minus 2z equals negative 11. So negative 2z equals negative 2. And z is equal to 1. Now, I have an x, I have a y, I have a z. Are those the actual answers? When I check this in the original equation, 2 times negative 3 is negative 6 plus a y of 2. That comes out to be negative 4. That's what I needed. Check the second one. Negative 2 times y. Negative 2 times y is negative 4. So I'm going to get negative 4 plus 4 times z plus 4 times 1, which is 4. That is equal to 0. So the second one checks out. The last one, 3 times x, negative 3. So that's negative 9 minus 2 times z, which is 2, is equal to negative 11. The third one checks out with these. So I have my answer. My x is equal to negative 3, my y is equal to 2, and z is equal to 1. That would be the solution, or the set of numbers that is going to solve this system. That's going to work in all three of these equations. Let's try another one here. Solve the system by using elimination. So what I see here, I see that with this part right here, those z's can go away. So I'm going to take this first equation plus the second equation. We're going to forget about that one for right now. This first one plus the second one is going to be 3x. If I add them together, these two, I get plus 2y. The z's go away is equal to 3. Now I look at this in conjunction with that last equation, the 3x plus 2y is equal to 0. Here, what I like to do, so that I can add, I might take this first equation times a negative 1. That way the x's will have the same but opposite. So negative 3x minus 2y, do it to this side, do it to this side, equals negative 3. I'm going to take these two equations that I've got here. I'm going to add them together now. The x's go away, the y's go away, and I get negative 3. Well, this is saying 0 is equal to negative 3. What does that mean? Like before, I got something that's inconsistent. This isn't true, so this is inconsistent. Meaning we are not going to find a solution that would work for all three of these equations. What would we do if we ended up with something that was always true? Well, then we would we'd have an infinitely number of solutions, and the infinitely number of solutions we could just solve for one of the variables, and that would give us our answer. So I hope that helps. Good luck, and let me know if you have questions. Almost to the end of the semester.